Hello, Debmalya.
Hello.
Hello.
Um, Hello. One
Ah,
second.
okay, okay.
Hello.
Debmalya.
শুনি পাইছা ন?
শুনিছো। তুমি?
মই শুনি আছো।
শুনি
আহ,
আছো। তুমি স্ক্ৰীনখন শ্বেয়াৰ কৰাচোন এবাৰ।
সেইটো ক'ৰ পৰা কৰে কিন্তু
প্ৰেজেন্ট নাও থাকিব।
প্ৰেজেণ্ট নাও ৰাইট।
আহ, আহ,
সেইটো মোৰ এটা উইণ্ড' ৰাইট।
আহ,
ওৱান ছেকেণ্ড। এইটোৱে হয়।
গ্ৰেট, গ্ৰেট।
আহ,
আহ,
এতিয়া যদি মই শ্লাইড শ্বেয়াৰত দিওঁ তেতিয়া মই এবাৰ চাই লওঁ।
আহ, 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 আহ,
Slide
আহ,
show.
কৰি দিয়া।
So slide show. Play from. Okay. So
Debmalya.
it এইটো আহি আছে ন?
It is fine. But
Okay.
it is blank. White screen হৈ আছে।
White screen.
Okay, fine, fine. Fine.
এতিয়া আহিছে ন?
মজা।
Okay.
अजय
यस बोलिए.
हेलो अजय
या
Hello.
टेल मी. हाँ बोलिए.
अजय when you'll do the like live
I've streamed it. I've streamed it. Actually, we are live now. Just
oh
streamed. Just streamed.
okay
Not a problem. We just can be a little alert.
okay fine maybe then Debmalya, let us wait for some time na
Yeah,
maybe
sure.
5 minutes. Okay.
Yeah, sure.
Okay, fine. Then we'll just
Yeah.
mute. Yeah, fine. Thank you.
Sure.
Hello. Uh, Let me check. Is the audio clear now? Abhigyan,
Yes,
can you
yes.
just confirm if the audio is clear now?
Yeah, clear.
You can mute now.
Okay, I'm just testing. Things are working okay. I just hope the audio is not echoing anymore. Like someone can just confirm this. Thank you.
No echo, it's clear.
Is it better if I keep my Google Meet thing sound on, or should I put it off? Maybe I'm just trying to see if that gives a better audio in our live stream.
Ajay? Hello? Ajay?
Hello, Ajahar, am I audible?
Yes, yes, you are audible.
Okay, so can you start now?
We can wait for Azahar's confirmation.
Okay, sure. So, I think we can start. Azhar, you there? Okay, so without wasting much time, let us start our first program. So, good evening. I welcome all of you on behalf of Team I to the program. Thank you everyone for being with us today virtually in this first webinar of Assam Artificial Intelligence Initiative. Assam Artificial Intelligence Initiative is an initiative to promote AI in the region of Northeast and to build an academic network for students, researchers, AI enthusiasts to exchange knowledge. The primary aim of this initiative is to create a sustainable AI platform for the students, researchers of Assam and Northeast region, and also to popularize AI among children, non-specialists of this region. Today, we are very happy to inform you that an Amazon Alexa scientist who has vast experiences creating conversational AI is invited to enlighten us on this topic in our very first I Technical Lecture series. He will also talk about the current trends in the AI industry and about the basic skills that one student should have to enter the AI industry. Let me introduce our respected speaker today. Debmalya Chakrabarty is currently working as an applied scientist in Amazon Alexa machine learning team. He has pursued his PhD from Department of Electrical and Computer Engineering, John Hopkins University, in the year of 2018. His area of interest is in trying to understand how brain perceives sound and build good machine learning models based on this understanding. His research mainly focuses at the interaction of machine learning and signal processing. He has published several research articles in various reputed journals and conferences all over the world. I welcome Debmalya to this session. Debmalya, you there? Debmalya, can you hear me? Please unmute yourself.
Yeah.
Yeah.
Can you hear me now? Can you hear me?
Yeah. We can hear you right. I hand over the session to you, Debmalya. Thank you for joining with us. You may proceed, please, kindly.
Can everybody see my screen?
Yes, it's visible.
Okay, good. 1 second.
Before starting off his presentation, I'd like to request all the participants to kindly put your questions in the chat box, and we'll take up your questions at the end of the session. Thank you.
Cool. Thanks a lot for the introduction. And so in this talk, I'm going to briefly discuss on the recent trends that are there in conversational AI. And right now I'm working as an applied scientist in Amazon Alexa lab, as she mentioned in his introduction. Thanks for that. And so let's begin with the talk. So before just diving deep into the conversational agent part, let me give a brief background on the projects that I have pursued over couple of years, several years, since the time I actually started my pursuits in the area of processing, and eventually it kind of got intersected with machine learning. So I started off my speed journey at IIT Guwahati EMSTL lab, where I was working as a project assistant from year 2011 to 2012. And I was working under the guidance of Professor SRM Prasanna, and I was working on the project, which was DIT funded, and the project was developing an online-based text-independent speaker verification system. And then from 2012, I joined Johns Hopkins University for my PhD program, and I joined the Laboratory for Computational and Auditory Perception Lab, which is headed by Professor Monia Elilali, and I was primarily working in the area of computational auditory scene analysis. I defended my PhD in 2018 May, and came back to India to join Amazon Alexa ASR Labs and started working on automatic speech recognition. So this was a brief an overview of what are the different things, the projects that I have worked on. So before starting on conversational agents, I would like to give a brief overview of what I was up to or what I was doing at the time of my PhD. So which was primarily in the area of computational auditory scene analysis. I thought that it might be a good overview of what I was doing, and then how I kind of got into the area of speech recognition. So just to begin it off, let me give a brief overview of what actually auditory scene analysis is. So just based on this picture that I'm right now showing, you can see that there is an orchestra that is getting played. And so when we are listening to an orchestra, an orchestra kind of comprises of different kinds of musical entities in the piece itself. like which can be like different instruments that are getting played, and also there is someone who might be singing also. So like for example, in this picture itself, there is someone who is playing cello, there is someone who is playing violin, there is someone who is maybe playing trumpet, and someone who are also like singing in the choir. So, however, when we actually perceive that sound, like it comes as a totality and falls on our ears, the way we perceive it is we can kind of like identify each of these musical instruments like separately, in a separated way. Like even if it is an orchestra, we can kind of focus onto each of the objects, right? And also, if you want, like we can now switch our attention to, say, for example, just the song itself. So when we listen to the song, we will see that the instruments kind of go to the background. Whereas when we want to listen to the musical instrument, we'll see that the song will go to the background. So that's how we kind of switch our attention from different objects from one another. So the brain typically does it very in a very like a trained way. So we do it like in a very natural fashion. However, when we want to build a system out of it, that is a difficult job, because the signal itself is like a composition of all these different pieces. So what the system has to do right now, any algorithm or model has to do is like it has to kind of break it down all into different objects altogether, like the sound objects. So it's a difficult thing. Now, when we actually look into the signal, it basically is nothing but a time signal, right? So this time signal, when we look into this time signal of for this particular orchestra piece, we can see that we cannot identify anything out of it. Even when we are actually kind of taking it into some kind of a like a time frequency representation, which is like a much more higher representation for compared to a time signal, we'll still see that yes, there are some of those like the structures present along the frequency axis, but still from this particular image, it's very difficult to gauge which particular frequency belongs to what object, or like say for example cello, or does it belong to a violin, or does it actually belong to the song itself. So I mean, we can see that from the signal itself, it's very difficult to gauge what is getting played, and that kind of forms the crux of what we were up to and what I was working on. So basically what we wanted to figure out was what are the basic sound properties that do help segregate an object into an auditory scene. And the second thing is like, how does, once we know that what are the properties that will help us segregating the object, how does prior knowledge about the objects itself facilitate auditory scene analysis? So there were like two parts to the problem, and we wanted to like tackle it one by one. So first we wanted to come up with a good representation of the sound itself that can help or that can aid segregating an object into an auditory scene. Like here, I'm keeping on using object. So basically, object is nothing but an auditory object. It's like, for example, the piano itself, the sound coming from the piano or the sound coming from the cello. These are like individual objects. And then once we have the prior knowledge about these objects, then how do we actually use this knowledge to facilitate auditory scene analysis? So the key strategies that have been studied in the literature is something like this. So we have the sound, and then we do a feature representation of the sound, and then we pass that representation to a background model, and then the task that is underlying that particular activity. For example, it might be a segregation task, or it might be a classification task, or even it might be event detection task. So it just depends upon what kind of task you are using. So the feature representations that have been used for this kind of studies are mostly like very generic or general features which have been used a lot in the literature, like Mel frequency capture coefficients, LPCs, spectrotemporal modulation features, and Gabor filters. I won't go in detail into the detail of each of these features, but these are some of the generic features. Anybody who has been working in the area of speech or sound might be very well aware with all these different kind of features that are there in the literature. And then once we know what the feature representation is, there is the background modeling. So background modeling typically can be a generative framework, which is like, can be a Gaussian mixture model, hidden Markov models, or can be a discriminative framework. So it all depends upon the kind of task, as I mentioned. Like if it is, say for example, a classification task, then you might want to go with a discriminative framework. But if even if, like for example, in case of classification, you might want to model it for each of the objects. Say for example, you have a lot of data for piano, and say you want also have data for music. So what you will do is that you just build some basic Gaussian mixture models for music and piano, and then you might do some kind of a like a likelihood test, and like you can come up with a good model to classify or detect the two. So any of the frameworks will work out. But the problem comes up when they are in isolation. Like we have individual data for individual objects, but the problem is when they are together. So then, well, all the problems like how do we actually devise techniques that can cater, or that can break down like a composite signal into like a multiple object. So then the task becomes slightly difficult. And here the task can be like a segregation, as I said, or it's a classification or event detection. Now, this was all about the engineering strategies. What, at least in my lab, or what we were also interested upon, is how does typically neuroscience, what are the neuroscience approaches? Like, for example, how do, what are the psychoacoustics experiments or physiological experiments that typically said about this kind of auditory task? So we also wanted to look into that and kind of come up with something that can combine the two words. So the thing is, like in neuroscience strategy, when we have a time frequency analysis, as you can see from the picture, we can see that we can just take these small snippets for across time. So you can see these red blocks basically comprises to certain time instances when you are taking a frame. It can be like ranging from 25 milliseconds to all the way from 1 second. It all depends upon how you want to do the analysis. And then these particular frames of sounds or the speech, they basically give us something like simultaneous processes. So what they say is that each of these blocks of frames can tell us something about the kind of object that is present within that. So for example, if we do an analysis on just these blocks, we can basically capture those instantaneous structures that are present in the sound, and that can cater to something like, for example, some specific object. Say for example, gunshot, right? Gunshot is something like a very specific or very instantaneous sound. However, if you consider music, music has something like a rhythmic structure. So these instantaneous blocks will kind of tell us what kind of the representation does the object has. But will it solve the entire problem? I don't think so, because there might be a lot of other objects which have similar kind of these representations. For example, piano and cello, right? So when you do a difference between the two, these instantaneous blocks might not give you the exact picture of how they behave over time. These are some of the processes that we have looked into, or even in literature they have been tried upon. For example, the harmonicity, the onsets, and the amplitude modulations, and the frequency modulation. But as I said, like these instantaneous sound structures will just tell about certain like very different kind of objects. But if you want to like say differentiate between two objects which are very close to each other in terms of their instantaneous behavior, what we want to look into is also how they behave over time. So that kind of captures the rhythmic structure of the sound, right? For example, music and piano might have a very different rhythmic structure. So if we capture that, that might tell us something about how these two different objects are different from each other. So this was basically some of the neuroscience strategies that we looked into, and the proposed strategy that we came up with was something like a neurocomputational approach, where we took something from engineering and we took something from neuroscience, and that kind of combined the two. So there was a deep belief network that we employed from the engineering side, and there was the simultaneous and sequential cue knowledge that we employed from the neuroscience approach side, and then we basically combined them together to form this framework. So the key questions that we wanted to answer was how the cues emerge from natural sounds, and how to learn those cues, basically those features, in a holistic way, and how those cues kind of facilitate auditory scene analysis problem. So this is the basic framework that we came up with. I won't go too much into detail of it, but there was this machine learning component that came up with. So what we actually wanted to do was, we have this sound, and based on this particular structure, which is the RBM and the multi-rate CRBM, what we wanted to do is that kind of capturing some kind of a global and instantaneous representation from the sound itself. And that sound is not restricted to just isolated sounds. It can be mixture of sounds. So when we train a network like that, it captures, as I said, both simultaneous and sequential cues, and it kind of gives us some kind of a representation which might be very diverse enough for different objects and help us to give some kind of a idea about how to kind of segregate these sounds over the space. So this was one particular approach, and then once we have formulated this particular framework, we also came up with something like a top-down framework where we took the crux of the framework, where, as you can see, that there was a RBM and the CRBM, and then we wanted to solve the problem of scene detection or scene classification. So what we had is that we used that here hierarchical structure as some kind of a embedding extraction, and then passed it on to a long short-term memory, which is an LSTM, and then used it for a classification of the label. So this is how we kind of came up, like we joined the engineering and the neuroscience approaches and proposed this particular framework. So the key ideas that we kind of got from this particular study was something like two things. Like one is like there is totally a way of acoustic driven bottom-up saliency framework, which is like bottom-up in the sense that we don't have any knowledge about the objects itself. What we want to do is that just want to capture the representation. It can be like those simultaneous and sequential cues that I talked about in the earlier slide. And then also there is something like a top-down approach where we have some knowledge about the object, and then we are using that knowledge to kind of basically change the framework, so that the way it's like, you can think of it like an attention. Say, for example, you are listening to a continuous piece of music, and then you are constantly switching your attention to attend to just one particular part of the musical piece. Say, for example, you want to attend to just the piano, but the way you have to do it is you have to first know what piano sound looks like or sounds like. Once you have that knowledge, then only you can attend to that. So that is the thing that I'm talking about. That's like a top-down attention. It's like you have the knowledge of how piano sounds like, and then you're attending to the piano. And similarly, you can switch to the song piece also, because so that's the differentiation I'm talking about in this particular framework. So that is like a bottom-up and top-down thing that I kind of worked upon during my PhD. So these are the key ideas that we came up with. So now that kind of brings us to what actually is the crux of this talk, which is like a conversational agent. So I will kind of spend some time in developing the overview of what actually conversational agent is, how it works, like what are the key components that do add up together to form a conversational agent. So first, a basic example can be like if we ask something to, say, Alexa or Google Home or anything, like say, for example, is it hot outside, then the machine or the device will respond it based on what it is actually outside. So it's sunny and warm, and then you kind of get engaged into a conversation with the device, and then say, for example, you develop that conversation, and based on that conversation, the device keeps on communicating. So the way it works is like it is built upon like multiple blocks, which are like, say, language understanding. Language understanding is first has to understand like what actually you are saying. So basically even like, for example, first it has to identify like which language you are saying in. Some of the languages might not get supported, so then the device will prompt that these are something that is not supported. So it first has to actually identify what, or like understand what is being said. So that it kind of becomes the crux of the first few modules that typically builds up a agent, conversational agent. And then it goes to dialogue management. Dialogue management is something like how the device is going to respond. Say, for example, I'm saying, is it hot outside? So then it has to first identify or understand what I'm meaning with the statement, and then it has to respond in a particular way, like it's sunny and warm. So that's the dialogue management part, like the response that it is coming from. Like before that response, like it has to first like route that particular like that conversation to certain part, and then it has to generate that response. And it's all happening based on certain knowledge structures that we are constantly feeding onto the device. Like basically to understand this knowledge for this dialogue management or even for response generation, these are all based on certain knowledge entities that are already training the system constantly. So for example, even this particular part of the conversation, the device has learned something, so which which it will use later in certain other parts of the conversation also. So now the basic the scientific challenges that typically come up in these conversational agents are, but the first thing is like conversation is a very hard thing, like because it's like a free form thing, right? So we can say anything and we are expecting the device to actually respond to that anything, right? So that's the thing, that's the free form conversation that we might want to have with any person. So we might want to have that with the device. Sometimes the device might be limited in certain way, but that's the limitation that we would like to address, or like we want that's the challenge, that's the thing that we would like the device to address. And then there is a like the language understanding, as I was talking about. Like first there is the speech recognition, and then there is language understanding, which is like understanding the actual semantics of what it is. For example, as I said, like what is the temperature outside, the device has to understand the meaning of temperature. So then only it will respond in a certain way, like it is 38 degrees outside or it is 40 degrees outside. So it forms its responses based on certain understanding, and that understanding comes with certain kind of knowledge entities that we have to pass on to. And then there is some kind of a context modeling also. For example, we would not want to like constantly repeat what you have already said. So for example, I have asked for temperature, so in that case the device has to respond, and then I might want to build up on that. So when you are building up onto something, then you cannot like you cannot expect the like the device cannot expect the like the customer to constantly keep him reminding that okay, I said something in the first part. So as I showed in the last slide, like there was some certain pattern to the conversation. So that's like the context, and that's how, like for example here, finally the conversation ended and I was thinking of hiking the dish, and there the device is responding like there is a 60% chance of rain, which means that the device has got the context of okay, this is the weather that has been talked about. So that's the context, and that's also an important part of any conversation, because we always work on context, right? So and then there is personalization and text to speech. So personalization is something like, for example, I have my device, some other person might have their own device and they might want to personalize it in their own way based on their preferences. So for example, I like sports, so I would like to have some specific sports specific kind of a news or some specific sports kind of updates, those kind of personalization I'm talking about. And someone might have a liking for music, so that's the personalization aspect. And then there is text to speech, because that's when the natural responses, the way the device responds back to you. So then that's the text to speech. So these are the different scientific challenges that are all from the crux of developing a conversational agent. And the capabilities is basically it can talk like if someone is using a device, they might know that it can kind of cater to anything about entertainment. It can do household things, communication, information, smart homes. So all are the different, these have all the different capabilities, but all these capabilities come with their own challenges as well. So now basically once we have understood what is a conversational agent is and what are the challenges there, so now it kind of comes down to the building blocks of a conversational agent. So it all starts from basically the ASR. So ASR is like at the forefront of this block. So you have the speech, and then the first thing is like the device has to do is like it has to generate a text from the speech. So the next are all downstream. So the next set of blocks basically will work on the output of the ASR. So if the ASR is somehow behaving badly or working badly, then all of the next set of blocks will basically carry over that error. So it's very important for ASR to work at least with a decent accuracy, because it is the kind of the forefront of any conversational agent. And then basically comes the next set of blocks, which are NLU, like language understanding and natural language understanding, which works on the text, and then it generates certain labels. Like for example, I am asking for what is the temperature. So then from this particular text, the NLU system will say that, okay, this is catered to something like a weather or something like temperature. So these are like basically the slots that we are looking for. And then once we have identified these slots, like it's a weather or it's a temperature, then it goes to something like a dialog manager, which will generate a particular action. So, okay, so basically say there is a dialog manager. Once it gets a slot like a weather, then it has a certain set of actions which has to take. For example, it will go and query a database which has got which is constantly fetching temperature from outside. So I'm just giving an example. So then it will go and query what is the current temperature outside, or what is the current weather condition outside. So it will generate those kind of actions. And once it has generated the action, then it is the device which will respond back. So, okay, this is the temperature, or this is how the weather is outside. So yeah, basically that's what is I have also mentioned in this particular table. So kind of like summarizes the entire block system of a conversational agent. So the common theme that typically lies in this particular in this kind of topics, or in this kind of work system, is data-driven machine learning, because machine learning kind of comes at each and every of the steps, and it all is data-driven, because more the data is, more better the system will be, because the system is constantly learning from the mistakes that it is making, but these are also based on the data. So the first three key things that any agent or any conversational system should be like dependent upon is probabilistic modeling, in order to make it more robust to noise and ambiguity, because we cannot expect someone to always say something in an extremely clean condition. There will always be some kind of noise. So it is the responsibility of any of the blocks that are there in an agent, the conversation agent, to kind of make sure that that it is able to deal with all this background or any kind of noise. And then also something like the ground truth creation, which is like also deals with the data part. Like to train any system, we need a label data, right? So for generating the labels also, there has to be certain, because we cannot always employ human to generate those labels, because it becomes extremely expensive to say, for example, you have to label say 40,000 hours of data. It is extremely expensive for human to actually do it. So you have to come up with certain machine learning approaches also to kind of generate those targets for you, or to generate those labels for you. And also there is also something like a portability or adaptability to new languages and domains, because there is always something that in this fast world, there is always something that is coming up. So and whenever there is something new, the problem is it comes with a very less data, because there is not, because it is new. Now the thing is, like, we have to make the system in such a way that it adapts itself very quickly to that newness of the domain. So it's like something like a low resource domain adaptation kind of thing. So those are the three key things that typically needs to be taken care of. And basically any conversation agent kind of works in these two things. If you look into the bottom figure, so there is like first the training, and then there is the decoding. So the training is something like it needs the input, and there are the truth, which is like the labels, right? And so you basically train the model, and then you have to infer something. So the model can be anything. It can be an ASR model, it can be an LU model. So just the input will change for the different models. For ASR, it will be a speech, and for NLU, it will be a text. But it's like the philosophy will still remain the same. Like it has to infer something from the input and give the correct answers. It's just that those answers will change. Like for ASR, the output is going to be a sequence of words, and then for NLU, like language understanding, it will be something like intents and slots. As I said, like for example, what is the temperature? Then if you pass it on to an NLU system, the NLU has to predict what is the slot there. Is it like a temperature slot, or is it like a weather slot, or is it like a music slot? Is it like an, say for example, play some music by A.R. Rahman? It has to identify what A.R. Rahman falls under. Like it should be an artist. Then only it will kind of go and make the correct queries in the downstream applications. So this is basically data-driven ML for continuous improvement, and this kind of becomes the major crux of how a conversation agent is constantly getting built and constantly getting deployed. So like if I will talk about each of the blocks here. So the thing is, like, first we have this time varying live production data, which is always getting generated by the device. So the first thing is data sampling. So we have to kind of first get the data, right, to train a model. So the data is constantly coming from the production itself. And what we do is, what any system does is, like, it samples those data at certain points of time, and then it does some kind of an active learning to which is like a confidence-based thresholding on the data, just to see that whether the data is good enough or not. Then it chooses the data from that set, and then it sends the data for ground truth generation. Either it can be human transcription, or it can be a machine learning model itself, but that data has to be passed on as the input to that. So once we have the input ready and the labels ready, then we basically pass it on to an ASR model training and an NLU model training. We can also use some kind of unlabeled audio as well, which is something like a semi-supervised kind of a training where you don't have the labels, but you can use the audio still for the training. So there are different mechanisms to do it. Once you get the models trained from this data, then you basically do some kind of validation of the model by doing some kind of a testing on all the models. And once the models are validated, it is deployed. So once it is deployed, that model will now generate the traffic. So then again, the process will kind of repeat itself. Like, you have the model deployed, we will start, like any customer will get the models, and then they will make the query to the new model, and then the data will get generated, and again it will come back to us, like, for this sampling techniques and all these things. So it's like a cyclic process, and it keeps on moving. But the thing is that the models keep on changing, so the kind of data that we are getting might be better over the years, because the model always keeps on improving. Like, we cannot keep on giving bad models. It's just that we have to come up with new techniques to improve the model, and then the data also that comes out of the model gets better and better over the years. So now I will try to shift my focus to some of the speech-related problems, because I am kind of working in the area of speech recognition. So, and I am primarily working in far-field speech recognition. So these are the major challenges that we typically face. One is like again the same thing, that it's noisy environment. So we have to deal with the noisy speech, and we have to make the system robust. And then there is a large vocabulary and high perplexity domains. For example, the new ones. Say for shopping. Shopping is something, it might be very new in terms of like the data. Like, people have started asking for shopping related queries, but the vocab might not have those queries in their in the data structure. So then what happens is that we have to use some kind of an adaptability technique to get the existing LM adapt very quickly to those new domains. So that is also one of the challenge. And there is another challenge, like difficult to predict spoken form for catalog entries and their associated pronunciations. For example, there is a player called Tsitsipas, and it's a Greek name, but he might be performing very well in, say, French Open, or like, say, US Open. So people might be making a lot of query regarding Tsitsipas, but Tsitsipas is a very less used word. So the so in terms of probability, in terms of machine learning, if you think it's something like an out of vocabulary word, so how to deal with those things? So that is something is also one of the challenges. And also then there is always this kind of problems like acoustically confusable titles like Sundays or Sundays. So those are the things that typically comes up a lot as a challenge. So I will quickly go through what exactly a speech recognition module is, and just so people get a basic idea of it. So basically, we have the sound, and so it's like it's a system that takes the sound or speech as an input, and the output is basically text. So that's the basic thing. Now there are different components which actually get involved while building a speech recognition system. So first, there's a feature extraction, which is like the common thing to all the machine learning blocks. You have to extract the features, and then those feature vectors kind of go into an acoustic model. So those acoustic model gives you some kind of a phonetic probabilities. Like for example, I have said like Alexa or say Google. So then it will basically divide those speech into certain phonetic units, and the acoustic model will give the probabilities for each of these units. So you have now, but this is like still at the phonetic level, like basic, very granular level. We want to go all the way to the words. So what are the other components that typically help is like the language model, which has those word specific information, and they kind of come up and they help these acoustic units to kind of form the next sequence of words, because it queries those language model constantly and gets some kind of a score, and based on the scores it comes up with the nearest words that can be formed with those acoustic units. Say for example, I've said increase to 70 degrees, so the word sequence will be increased to 70 degrees. And then there will be some kind of a post processing also based on what are the downstream applications. Say for example, the downstream application is expecting something like 70 degree. So then we have to do the post processing also, because otherwise the downstream will fail. So this was the basic building block of a speech recognition module. And then there is something like a semi-supervised speech recognition training as well. I might not go like too detail into it. Like just a basic idea is like sometimes what happens is we might not have a very because these are online systems. So architecturally they are limited in the sense that we cannot like use a very huge machine learning block into an online system, because otherwise the latency will be very, very slow. We are asking something and it might respond after 5 minutes, which we will not want, right? So we have to make sure that the student model that we are employing onto is like a some kind of like a low architecture, low power using model, but can work at a decent accuracy. But to improve the performance of the student, we can make use of something like an offline, very powerful model called teacher, which can be trained on same amount of data, but it is accuracy will be very, very high compared to student. So based on this accuracy graph. Now what happens is that we also have a huge amount of unlabeled data that is there in the production, right? So what happens is that we can use that unlabeled data, use the teacher to generate the labels for this data, and then use it back into the system. So you are kind of increasing the data, the data requirement for the student model, but the way you are doing it is like you are leveraging a very powerful offline teacher to generate the targets for the data, and then you are using it in the training. So in that case, the student performance really, really improves. And this has been validated experimentally in our experiments also, and it has been well reported in the literature as well. So now once we have the like the acoustic modeling setup ready, now the thing is like we have to go to a language modeling. As I was saying, language modeling plays a very, very important role in getting the in ASR system up and ready. So one thing is like there is like conversational free prompts are extremely high perplexity. So by high perplexity, it means that basically we can say anything, right? Like the customer or the consumer is not restricted to what you want to ask Google or Alexa. We have to like it can be a free form kind of a conversation. So for those kind of a conversation, language model has to be inherently high perplex, like it is inherently high perplexity. So now to kind of cater to this free form kind of a conversation, we have to increase the language model capacity a lot. Like we have to increase the vocabulary structure a lot. Like for example, say you earlier had 100 unigrams, but now to cater to this kind of free form kind of a conversation, we might have to increase the n-gram to like say 100,000. But in that case, what happens is that it significantly increases the latency. So those are the latency is one of the very key things that we have to keep in mind, because we don't want the device to respond in like say like 100 seconds or 200 seconds, because that again will lead to customer dissatisfaction. So we have to make sure that we have to need some kind of a new representation for n-gram language models and decoder that is capable of accommodating large increase in LM size also can support this read from words. There also has to be support for specific low vocab domains. For example, the shopping that I was referring to in previous slides, and also contextual LM. For example, I have said something and then I want to carry over the conversation. So I don't want any of the agents to kind of forget what has been said like previous 5 utterances. So the context always has to be carried over. So those are the challenges that a typical language model has to face. And there are like a lot of research directions that typically get pursued in each of these directions. And then there is also, I was also referring to something like a personalization, where I want the device to basically work according to my setup, and someone wants to in their own setup. So that also like speaker adaptation plays an important role in that, because like speaker adaptation is something like you have, because when we are training a model, we are not saying that, okay, respond this way to certain speaker and this way to other speaker. It is trained in a unified way. But speaker adaptation is something that you can change something architecturally, the way the model is learning, and you can make sure that with a certain less amount of data for a particular speaker, the model adapts very quickly to that speaker voice. So that is like a speaker adaptation. I'm not going into the detail of what iVector is, because iVector is something like a very common way of generating these speaker adaptation modules. But this is something that gets typically used across these things to basically make sure that the agents or the conversation system typically adapts to a particular speaker. But this is heavily used for personalization things, because I want the Alexa to like identify my voice very perfectly. So that's why this speaker adaptation like plays an important role, and it has been validated experimentally as well. And then there is an important thing called speech endpointing. So the speech endpointing is like the final module of a ASR, like the ASR block. It's the final module of that. So what happens is when there is an end of speech, because NLU system also has to come into the picture very quickly, because there is an overall latency as well. So endpointing plays a very important role in triggering when the NLU is coming into picture, because it kind of detects the end of speech, and then NLU, as soon as there is end of speech detected, NLU system with the output will be sent to the NLU system and it will be triggered. So there is a latency there as well, and we want to reduce that latency. So the way we want to do it is like we want to like make use of certain acoustic as well as linguistic informations as well. For example, there is an example said play music by, there is a certain pause, and then sting, and then there is a certain pause. Now, if you see that there is a pause in the middle part also, but I don't want the endpointing to trigger at this point. So the way it can be done is that if we have some kind of a linguistic information, because when there is a by, it is expecting something also to come later. So acoustically it is difficult, but linguistically you can give. So there is some kind of an LM score. So the low end of sentence probability is low, which means that the probability of triggering the endpointing will also be low in this case. But as soon as the artist like sting comes, and then again the LM score is re-evaluated, it says that okay, now there is a high probability to generate end of sentence, and then the end probability of triggering the endpointing also becomes high. So this is how the typical endpointing is kind of like triggered across various conversational agents, and by making use of both LM as well as acoustic information also, because acoustic information is also important because of these pauses, right? So that's what I mean. Now there is another thing called anchored speech detection, which is something like when I am talking to Alexa or Google or any other Siri, I don't want like the background noises to play an important role. Say for example, there is someone else who is also talking in the background. Like for example, there is like Alexa play music, and then there is someone saying take the dog out. Now I don't want I don't want like the endpointing to get triggered after the take the dog out. The endpointing has to get triggered after play music. So the way to do it is like some kind of a speech detection techniques, but by anchoring to certain words. This also has has to take information from both acoustic modeling as well as language modeling, because the language modeling also will say something about, say there is a play music and then there is an end of sentence probability. So that probability also plays an important role. So this is like anchored because this is anchored by certain words which are typically at the end of the utterance, and it plays an important role in making the device directed to certain speech. So this was all about the ASR, the different volumes or different modules of ASR framework that typically works in a conversational agent. There are other blocks as well, as I mentioned, like there's NLU, and then there is like dialogue management. But I am primarily working in ASR, so I wanted to give a brief overview of what are the different building blocks of an ASR system that typically works in a conversational agent. Now, this is some of the work that I am right now working on. I just wanted to give a brief overview of what is that. So it's typically I'm working in the area of acoustic modeling, and the basic idea is like to kind of train a system which is very robust to like different kind of dialects. So basically making a system unified as so that it kind of is like very robust to different dialects or any kind of dialect, because dialect plays an important role in how the like in the ASR system works. So the way we do it is like basically, yeah, this slide is slightly busy, but I will very quickly go through it in the sense that, so there is like there is that pipeline that we typically work on, in the sense that there is a labeled pool data, which is like the data that is pulled across all the locales that we cater to. For example, it can be US, it can be India, it can be GB, Australia, everything. So we pull data from everywhere, and then we do some kind of a training, which can be a CTC training in this case, which is a connections temporal classification, but it can be any training. Like I'm just giving an example here. And then once we do that, we do basically take that model and then we fine tune on the locale specific data, and then we do some kind of a sequence-based training as well. But these are all done on labeled data. What I was focusing on, I am focusing on currently, is like how to make it like slightly better in the sense using some kind of a semi-supervised learning information, because in this kind of architecture, the problem is always the availability of labeled data. And labeled data is something which is like very expensive to get, because it needs a lot of human effort to generate those targets. So what happens is we don't have enough labels. So then we have to go to unlabeled data. So I'm primarily working on how to kind of get the unlabeled data into the picture and use that unlabeled data at each and every stage of the training pipeline, and make sure that the final system that we get is much better than the baseline system, which is basically on labeled data. So this was all about the conversational agents, like that typically the way they work on, and what is recently I'm focusing on. Now I would like to dedicate some time to also, just because there's an audience who also wants to know like what are the recent trends right now, based on, so this is based on what I have experienced, because my experience is also not that great, like in the sense that I am in Amazon for last 2 years, 2.5 years, and before that I was also studying. So I mean, this is just based on like my 2.5 years of experience. Basically the source is also here. So I mean, if someone wants to do a deep dive into it, then they can actually see the source. This is a very important, informative source that I came across, and I have kind of taken that picture from that particular source. So the recent trends right now is basically what's happening here is there is a big focus on the data science aspects of things. So the primary thing is like the automation. So everything right now is trying to move towards automation, because of the fact that the data is available in abundance, and we want to make use of the data at each and every aspect of like an organization. For example, recruitment. If an HR wants to like select candidates based on certain profiles, then that is also now AI models or like ML models to kind of trigger that. So that's where the automation is basically coming into picture. So there is a big focus on the driving systems towards automation, and that's where most of the like these jobs are also getting created, a lot data science specific jobs. So that is one thing. And then obviously there is the chatbots and all the emergence of this chatbot. For example, recently you might have known that Flipkart has also started voice search in their like search thing. in their shopping thing. So it means that they have also kind of realized that speech or voice is getting big and big in India, and there is a huge market for it. So advancement in NLP and conversational AI is also one of the key things that companies have started exploring. And then there is also big basically focus on explainable AI, which is something I find very interesting because of the fact that most of the machine learning models that that typically gets used a lot are used as black boxes. So for example, a typical machine learning model or any machine learning model cannot fit very well to all the tasks that are available in the world, right? So we have to know which model fits best which task. So that's where the explainability comes into picture. Like we want to know, like for example, a particular model, a particular ML model fits well to a particular task or not. And for that, the model has to tell us something in terms of its like performance over certain data. So that those are the things that basically companies are also started focusing on, in the sense that the primary reason being that we cannot like keep on treating the ML as like some kind of a black box. We at certain point of time we have to know what is actually going inside, and then kind of make a very informed decision whether we want to go with this model or not. So these are some of the trends that is right now happening. That at least this was what was reported in 2020, and I think this the trend will be there in 2021 as well. Right. So now, just wanted to give a brief perspective of what a real-world ML system is. So this is something that I found from this particular paper that was published in Names in 15 by Google, and they have given. And I would recommend everybody to once go through this particular paper because it was really, really good. So what they are actually saying and what actually true is, when you are building a real-world ML system, so there are a lot of key components that come into place. Like for example, there has to be a data collection framework. There has to be a data verification framework because all the data is not good, and some might be junk. And what it like, most of them are junk. So yeah, ML always follows a rule like junk in and then junk out. So if you are giving junk, then it will output junk. So verification is one of the key blocks that has to be there. And then there has to be something called like a machine resource management. There has to be infrastructure for machines like GPUs, and then there has to be process management tools, in the sense that the verification of the models. So those are the things which kind of make a real world ML system. And you can see that the black box, the ML code. So that's the small component that all comes into the picture here. So what I mean from this thing is that like whatever we learn or we do in the sense outside might play a very might be a very small component in the entire scheme of things. So these we also have to be very mindful of the other blocks as well. Like for example, the importance of the data, like whether the data is good or not, because most of the times we don't pay enough attention to how the data is, like whether the data is biased or not, whether the data is in the sense caters to what we want or not. So anything, if you use anything, the model is also going to give anything. So that's the thing. Like those are the key things that we should always look for, study in the sense that at least try to process before like kind of like making sure that okay, fixing the data, fixing the model, and then do the experiments. So that's why this particular this was important, at least in my opinion, because this is something that we don't typically look for a lot. And then there's also one important talk that I found in the YouTube by Dr. Om Deshmukh at IIT Bangalore, Triple IT Bangalore, sorry. So he was primarily again focusing on like the data problems, like in the sense that for building any ML system, how much important is the data? So basically, from the point of like capturing the data, and from the point to the last point of like what is the insight that we might get, which are actionable, that will bring value to the company. So there are different components. Like first, you have to capture the right data, which are relevant, which are granular, and then which also will contribute to user experience. Then we have to also think about how to store the data, because data might be available in like millions, because there's a lot of data now, but how to actually store it. So how to or use the data efficiently for model training. So, and then there is something called data processing. For example, how do you kind of also massage the data, like extract all the meaningful information from the data and leave out the junks. So those are the things that are very, very key in terms of like building a good ML system. So that is what I like also want like the audience also because I have not done this when I was in during my PhD, but this is something that I have learned a lot while working in the industry, because data is something that plays a very, very important role in terms of like driving the correct results for a large scale ML system. And then the finally the skills that we typically need for data science. Like in my view, like in the sense that like I can just talk from my personal experience. So what or like for example, when I was doing my PhD, how my advisor was saying. So basically, and but this is like a very personal, like someone might have a very different opinion as well. But so that's why, like there's a disclaimer to it. So one thing is like one should have a basic knowledge of linear algebra, probability, and statistics, because it's important in the sense that when we go to machine learning system, all we deal with is the matrices. In the matrices, then we would deal with the probability distributions. We deal with whether they are significant or not significant, the results are significant or not significant. So there are different kind of tests that you have to do. So these all kind of comes under these big umbrellas of algebra, probability, and statistics. These are the key things that I believe are important. And then definitely there is one language that like one should master upon in terms of coding. The reason I'm saying is that because I was the one who was not very, in the sense, good in coding when I was actually doing my PhD. So PhD is something which is like which is very dedicated thing, like in the sense that you work on a project and you keep on working on that. So you might not need the aspects of coding a lot. Like for example, in my case, MATLAB did all the, like I coded mostly in MATLAB. So but the problem is like coding in MATLAB might be very, very different than coding in Python. So that's why this is all coming from a personal experience, in the sense that one should always focus on getting some good hands-on experience on one particular language if someone has an aspiration of going to an industry, because that will be very, very helpful. And this is something that I have learned from experience. And then there are definitely the machine learning concepts, which both theoretical as well as practical. So there is an ML breadth, which we mean by ML breadth is like one should have a diverse knowledge of varied ML concepts, both classical and deep learning, because you never know what kind of ML system works for which kind of data. So it's always better to get a like a breadthful knowledge of different ML concepts. And then definitely there is ML depth, which means that we might know how an SVM works, but we might not know like how an SVM what is the mathematical framework of an SVM. Say for example, how we design the cost function, or like for example, what might be the convexity like constraints that determine how an SVM will work, or for example, what is the duality problem. We might not require it when we are coding it, but it's always important to know about it, because what if like the SVM is not working best for particular set of data. So we don't know whether this is because of the data or this is because of the inherent problem with the SVM itself. For example, the outliers for example, the hyperplane that we are building for the SVM might not be the best like the parameters we are training for that particular network. So in that case, the theoretical knowledge of SVM plays an important role. Like I'm just using SVM as example, but it can go with any of the ML system. For example, it can go with GMMs, it can go with deep neural nets, anything. So a basic depth of these systems are important. And then obviously problem solving, like in the sense that what understanding various aspects of building a basic ML system, that can lead, as I already said, that the relevance of data, how to avoid bias in the data, using an appropriate ML technique, understanding the pros and cons of different techniques, and making sure that this particular technique works best for this particular kind of a task. For example, if you are just building a fraud detection system, deep neural net might not be the best. We might want to use it because it's fancy, but say for example a basic SVM might also work. So that's the thing, like, because SVM is also discriminative, neural nets are also discriminative in nature, but SVMs might work pretty well, or say even a decision tree. So those are the things, right? So that comes with problem solving experience. And then obviously dealing with unstructured data, because most of the data that is lying out there in the world are unstructured in nature. Say starting from video, audio, starting from text, they're all unstructured. So we have to first kind of have to learn how to deal with this kind of unstructured data, in the sense that, as I said, like massaging the data in such a way that it forms certain kind of a pattern, and then applying it to ML frameworks. So yeah, these are the, I think, four key things that I believe might be an important skill for data science. But yeah, as I said, like it's just coming from the limited experience that I have. Someone else might have a totally different take on it. So yeah, this kind of brings me to the end of the presentation. Thank you.
Thank you, Debmalya, for your informative session. We are ready to take up some questions. So questions are coming up in the live chat in YouTube. So let us take the first question. Robert Patrick has asked, AI research in the field of music is perhaps less popular. Is Amazon currently working on music AI interaction for tasks such as creating AI generated music, automatic lyrics generation, etc.?
Yeah, so Amazon right now is definitely working in the area of music, but it might not be something like an automatic lyrics generation. It's primarily mostly from the idea of like music synthesis, and also in the area of, say for example, event detection. As I said, like for example, when you have something like a continuous stream of sound, and then you want to detect certain points, certain events, so music might be one of the events that you might want to detect, and like the Alexa might like get activated in certain way. So this is just some of the topics that typically get worked on. I think, yeah, that's also to my limited knowledge, because I'm part of just one component of Alexa. There might be a completely different team which might be working in Amazon, because it's a big company. So yeah, that's based on my limited knowledge.
Okay, thank you. And he has also asked, can you please share with us the differences between your research experience working in academia versus industry?
Okay, so yeah, that very good question, I would say, because academic research is, I mean, it's completely different compared to an industrial research, because in academic research, you know what the project is, and you are constantly working towards those projects. And I think the key also motivation is kind of getting some good papers out of it and getting some good insights out of it. That's the primary thing, because you want to contribute in certain way to the community out there. So you want to basically you are asking a question and you are trying to find an answer to it, and you are reaching that answer by certain basically research modules that you are designing, and then you are publishing it in the community. But in industry research, what happens is that the goals might keep on changing very, very quickly, because industry works at a very, very faster pace. So for example, the project that you like I might be working on today might be like it might change maybe in 4 or 5 months. So the goals are also very like very focused, and you have to kind of achieve those goals in very, very like short period of time. So there is something called long-term research, but there is also like a short-term research, because you want the product also to move very quickly. So in that case, you also have to be a little bit pragmatic in taking the approach that you might feel that, okay, it can be achieved in say next couple of months. So that might not be the most novel technique, but that might be the most pragmatic technique. So you have to basically make the decision, which is completely different in terms of academia, because you will take the novel technique, but rather not take the pragmatic, because in that case, it's difficult to publish.
Okay. The next question is from Subrat Datta. What are the standardized way to evaluate the model when it comes to generative architectures? and also about architectures used in language modeling.
Right. So generally in language modeling, so the way you tend to like evaluate the model is primarily by I think perplexity. Perplexity is something that kind of gives you an idea of how good the language model is, because the language like higher the perplex, like basically that kind of gives you how good the language model, in the sense that that is the score. And also there are this new set of generative like this new set of BERT and GPT-2, all these techniques are coming, so you also measure the blue score and all these things. Now I think that also comes under NLP, but it falls under different tasks that cater to NLP. Now, at least when we are building a ASR model, but what I would say is that based on my experience, though I'm saying that perplexity is the score that determines how good the language model is, but until unless you get the WER, you might not get the full picture, because a very good model in terms of its perplexity might not fare very well when you actually build the entire ASR model. So I would say that whenever someone is working in ASR, at least, I think word error rate might be the best metric. But if someone is like restricted just to language models, but then yeah, these are the scores. Yes.
Okay, thank you. Shishir Kolita wants to know about the challenges of building conversational AI agents in the context of India. Challenges of building conversational
Okay.
AI agents. Yeah.
Yeah. So so the major challenge is basically the data. I would say, Sishis, because the thing is that I mean, India is a multilingual nation, as we all know, and the thing is that the data present to for certain languages might be very less in number, less compared to a data, say for example English, because for example even in context of say any conversation agent, we might ask in our in English a lot, in the sense that even in case of Alexa and Google also we tend to use that. So there is a data sparsity across different languages, even for example in terms of say Hindi availability, or for example something like a Bengali, or say for example Assamese. I mean, there is a difference in the data available that is available to us. The primary reason being also is the text, because there might be a lot of text available for certain languages, but we might not have a lot of text also in the other languages. That all comes under the gambit of, like, in the sense, like for example, if you're working in an industry, because there are some propriety also that you might not use these particular resources for model building. So I mean, all in all, what I'm saying is that data sparsity is a very important, is a major challenge that we face, and it is very difficult to kind of build individual models for individual languages, because that will just increase the model overhead, right? So you don't want that. You want to build one model that will cater to all the languages. Now the problem when you are doing that is, when you are building one model, it is always being biased by a data that is available in huge quantity, for example the English or Hindi. And then as soon as you do that, then you have this problem of like adaptation, or then trying some techniques to kind of also make the other languages come up in that. So you can use some kind of technique like SSL and all these things, but again, like, that is something that is still not solved. It's not a solved story, and that is some of the challenges that at least I have faced in my experience.
Yeah, thank you. Next question is from Ruchita Somani. Can deep learning encoder decoder model be used for feature engineering part?
Yeah, I think. I mean, so yeah, it all depends upon like the way you how we want to use it. It definitely can be. For example, say as I said, like you want to incorporate certain kind of a context in ASR, or like for example any of the tasks, like context in the sense that say I want to basically build something like a shopping kind of a system which will cater to certain shopping domains. So what I can do is, like, I can train a model offline, and I can generate certain embeddings in that sequence to sequence model. I can use those embeddings back into when I'm actually training the network for the ASR. So those embeddings will kind of like guide the model to some kind of a domain adaptation, and also like guide the model in towards shopping slightly. So those are the things that can be. So I'm basically considering embedding extraction as some kind of a feature engineering, because finally you have to embed like concatenate those embeddings at certain point of time with the actual representation, which might be either the LFB features for acoustic, or say for example the n-grams or something for the language model. It can be used for, it can also be used for rescoring. For example, you have the language model and then you want to rescore at the final stage, then also you can use this different language model and different embedding representation, and kind of use to rescore it. So these are different stages where you can use it, and I think, yeah, I mean, it can be done.
Yeah, thank you. There is another. There are a couple of more questions coming up. Pritisha Barik wants to know: is there any algorithm that helps to distinguish between vowels and consonants in the waveform signal? It's from speech background.
Sorry, can you repeat?
Yeah, is there any algorithm that helps to distinguish between vowels and consonants in the waveform signal?
Yeah, I mean, yeah, I have to think about it. I think there should be vowels and consonants in the algorithm space. Okay, I mean, is it like, I mean, I think by machine learning we can do it, because there will be a lot of data available that will have just the vowels and the consonants, and I think that can be done. But is it like is it do you want to do it in a real time, or is it like just a classification system that you want to build?
Okay, Abhigyan Ganguly wants to know, can attention mechanism be helpful in speaker recognition or small duration ASR?
Oh yeah, yeah, right. So attention mechanism, yes, is very helpful. Definitely in short duration ASR. Yeah, the primary, I mean, attention mechanism is, you have to basically look at, if you're looking into a sequence to sequence model. So typically attention might not play a very huge role in the acoustics, because I mean, you might not want to, like, for example, you are saying certain phonemes at certain point of time, you might want to just go maybe 3 or 4 frames back to get a context. So you might want to attend to it to get that context information. But like certain few hundred frames back, I don't know how much that will add up as the information. But definitely in the decoding part, like in the encoder decoder, in the decoding part, because there the attention plays a huge role, because a decoder has this problem of like forgetting the context very quickly. So there is like a catastrophic forgetting problem, and attention definitely can help in that. But the major problem with attention is like the how much attention you want to add to the system, because any attention that you are adding to the system is always going to add to the latency of the system. So we have to basically make this judgment of how much attention you want, and also based on the performance that the system is making. But definitely it will help in the in the ASR world, like short ASR, because there are a lot of papers right now out there. Even Google, Facebook, they are all working in like transformer-based attention systems. But the streamable framework is yet not available. But definitely like full attention, which is far better than any BLSTM-based model.
Thank you. One last question from the YouTube chats. Pritisha wants to know how to, I'm unable to understand, but how to connect digit recognition from isolated digits in speech recognition. I think the question is not clear. How to connect digit recognition from isolated digits in speech recognition?
How to connect? I mean, you're saying, but that's a basic. I think it needs a longer discussion on it, because I think
right.
what she means by like you have individual digits, but now you want to connect them to make a sequence or something. I think there might be techniques available, but yeah, it needs a longer
Yeah, definitely. So there are some couple of questions in Google Meet chat box, so I'd like to take them. Jafir Shah is asking, suppose I'm conversing with a stranger and I do not know what to say next. Can I build a model to predict a next topic to talk about, looking at the previous conversations we did before? Can you throw some light here? I'm not talking about language modeling here. Debmalya, you can also see the chat box in the Google Meet if you want to read the chats directly.
Okay.
Yeah, it's on the Google Meet.
Okay. So
Yeah.
yeah, and I don't know what to say next. Can I build a model to predict a next topic to talk about? Looking at the previous conversation we discussed. So some light here, not on language modeling. I think we can do. I mean, in the sense that, say, for example, you can think from the aspect of like a sequence to sequence model from here. I'm not saying from language modeling, but say you have a sequence to sequence model, because you have a sequence of frames and then you also have a sequence of you have a sequence of basically the word pieces, right? So the thing is that, and you might also need some kind of an NLU information, but from the time being, I'm forgetting you don't have any NLU information. So say, for example, you build a system like that. What we have to do is that we have to build the recurrent system in such a way that basically we also keeping, like, it's like a state maintenance problem. We are assigning certain states to the constant sequence of words, and we are not allowing those states to get lost. So basically, if we are maintaining those states, like the decoder states, such that it from the acoustics, the mapping is such that it is kind of keeping a track of the previous words that have been emitted. Then based on those, we can again build a model in such, like, we can kind of make a sense of what is the topic. So it's also, you have to also integrate some kind of a topic building, like some kind of a Dirichlet mechanism here, which can identify from the from the word pieces what kind of topic. For example, there are certain words that will cater only to sports. Say, for example, you're talking about Virat Kohli or you are talking about AB de Villiers. Then there might be some mechanism from those states. You can kind of, there can be parallel network which will predict the topic from there, and then you can kind of come back to the topic if you want. So I mean, that's why, like, it has to be a two system in parallel, ASR as well as a topic modeling, but you can reuse the states from the ASR and feed it into the topic modeling and then get the output back into the ASR. So I mean, that's why, I mean, we can discuss it further, but this is some idea that we can talk about.
Yeah, the last question of this session from Abhishek De. First question is how Alexa ASR deals with out of vocabularies and phonetically confusing words. This is the first question.
Right. Actually, yeah. So that's the thing. Like, I cannot reveal very technical details about how Alexa ASR works because of, definitely, I mean, I think you guys will understand there's a proprietary problem with that. But in general, what I can say is that, right. So in general, typically for any conversational agent, in order to deal with OVs, the thing is that there are always certain basically there are always certain FSTs which can work. Like, for example, say, in the sense, you are talking about a French Open match, and as I said, like Tsitsipas, right? So Tsitsipas is something that is not there in the vocab that we have for ASR, like, because it was not used. Typically, the vocab is generated from the data that we have seen before. So the way to handle it is basically you can have certain FSTs particularly written to cater to those out of vocabulary words, in the sense that basically and the way you can build is like based on whatever trending you are seeing for that particular week. So it can be movie, it can be anything, because a new movie might not be there in the vocab, but we might know from a lot of other sources. and we build an FST out of it, and you just have to basically invoke that FST at the time of constructing the decoding graph for ASR. So that if that word is present in that particular FST, it can come up as some certain score in the decoding graph, and it will pick that up. It might not solve all the OVs out there, but definitely might solve the certain words that are very trending out there. So that's how typically we can deal about it. And also there is certain thing called model optimization is carried out in LSI for speeding up real time inference scenario. So yeah, so in terms of model optimization, that's the thing, right? Like it's mostly, it can either come from like so basically how you construct the final graph. At the end, there are a lot of different techniques to actually do that. I mean, you can find it out in like papers, for example, how you can make a very fast FST graph search to make some kind of a real-time inference. Also, you can do it also at the acoustic modeling side by, for example, CTC. If you replace CTC with, like if you replace a frame level decoding with a CTC, then also your inference time decreases a lot, because CTC is now working at a sequence level, whereas in frame level you are actually looking for each of the words. So those are the different technological as well as certain engineering changes that can be made to improve the speed of the inference time.
Okay, that's the end of our questions session. So from the host, Ajahar, do you want to say something here? Any questions from the participants? You can unmute yourself and ask the speaker directly. So I suppose there are no more questions. So Debmalya, thank you so much for your informative session, and thank you for gracing this session with your lots of your knowledge and your know-how on this topic. And we'll definitely look forward to more sessions from your side in future sessions of our initiative. Thank you so much for your precious time. I hope you also loved it. And
thanks a lot for inviting me and like giving me this opportunity to kind of share my experiences with a larger group.
Thank you so much, and please keep connected with this initiative, because this is our first talk that we have started from today itself, and hope we will get some more informative talk sessions from your side as well.
Definitely. Sure. Thanks a lot.
Thank you so much. So dear participants, we have come to the end of our session today. Thank you so much for your kind attention, and we hope to see you all in our next in our technical sessions that are coming up in the near future. So please stay connected with the initiative. The informations will be available on the page, the Facebook page.
I think
also,
I've heard it all. I mean, it was very interesting. Yes.
Ajahar, you want to say something? Okay. So thank you, Debmalya. Have a good evening. Thank you all.
Thank you. Good evening to all.
Thank you.